So welcome back to this YouTube channel. So in the last video, we have looked at a specific object detection model or object detection architecture, which is called RCNN, regional CNN, right? So we used, a selective search algorithm, to propose some regions, right? So this selective search algorithm will propose some regions, possible regions, and then we are going to input these regions to a machine learning model, a neural network or CNN, and the CNN will return whether the CNN will detect the IOU of uh, that object with respect to the actual prediction, right? So we'll just, in other words, the CNN will detect how good that prediction is. So in this video, we are going to look at one of the most used um, architecture in the field of object detection. That's a YOLO is an algorithm which is like very powerful, and almost like there are a lot of advancements in these fields of YOLO, right? So we have YOLO 8, version 8 also. So we are going to cover the theory, what is the basic things, and like this architecture is actually surprisingly simple. You know, we are going to learn what is the performance, what is actually happening under the hood. So first, this is the research paper, by the way. I think I'll put it in the description so you can read it. And all right, and then as you can read here, all the introduction, you don't have to read the introduction. So I'll just go through my whiteboard and explain what the architecture is, what are the inputs and outputs. So I'll just so YOLO algorithm, you only look once, right? So the idea is, I have already shared this idea in this last video, but I'll cover it again. So let's say you have an image. Let's say you have an image. So what the idea of YOLO algorithm is, we'll just divide this image into specific sizes. Let's say rectangular or square boxes. Let's say you have many square boxes. In the research paper, they have used these 7 by 7 square boxes. So in this whole image, you're going to have 7 by 7 small parts. You just divide this image into 7 by 7 small parts, and then you are going to run each part through a CNN model. And then I'll just tell what this CNN model predicts. So for each grid cell, for each grid cell, we will predict some number of um, outputs. So let's say the image, this is the object. Let's say for simplicity cases, let's say we'll deal with only one image or one object. So for simplicity cases, you can easily generalize because of this simple architecture. And then what will each grid cell predict is, the CNN for each grid cell will predict some parameters. I'll just write them first and then I'll explain it after. So we'll have X and Y and W, H, and then the confidence score, and also the class. These are the main things. Um, I'll explain what this is. So, like, relative to each cell, first, what are these X and Y's are? So X and Y here, the first variables that will be predicted by this CNN are X and Y. So these X and Y are the coordinates of a midpoint of the object. The model or the CNN for each grid cell will predict the overall width of the object. So we are going to predict a number which predicts the overall width. So for each grid cell, we are going to predict the overall width and the overall height. And look very closely. This width can be larger than the grid cell. So we are going to predict probably what is going to be the width of this object that is on this grid cell. So based on this input, we are going to predict the overall width. So we are going to get a box, right? So we're going to get, this is the width, we get, this is the height. So we'll probably get a box. So each grid cell will predict a box like that. So let's say this grid cell predict this box, and this grid cell maybe predict some other box, and based on that, we'll get some collection of boxes, right? And then also, not only that, we have also this C, or probably the confidence score. This C determines how, like, if there is an object in this area. So there can be many grid cells in which there is no object in that grid cell. So in which no object is intersected in that part of the grid cell. If there is no object, then the grid cell is going to be 0, the C is going to be 0, and otherwise C is going to be the nothing but IOU. So it's actually prediction of IOU, like how yeah, the confidence, like how probable is yeah, how probable, like the probability of that object being inside that grid cell, or the bounding box being around that object. And then we are going to get many number of grid cells. So that is a basic idea, and then based on that we will use what that non-max separation. Let's we'll use, I'm just going to show it. We're going to use non-max separation to remove and get the actual predictions. Hope you understand what's going on, right? So we'll for each grid cell, so we look at this. We're going to get we're going to have S by S grid on input. So this is just the visual explanation of what I did just now. So we're going to have this this image divided by S grids. In this paper, they have used 7 by 7 grid cells. So where these boxes are 7 by 7, S is equal to 7. And then we're going to have two outputs. We're going to have class probabilities. And yeah, I forgot to mention, not only this vector, but we'll also have the class probabilities. So big C. So class probabilities is nothing but the possible class. So for each grid cell, within this grid cell, we are going to predict what is going to be the possible class. So let's say you are going to have an object detection that can detect faces between my face and another person's face. We are going to have all these outputs to determine whether there is a face on this grid cell, and then we're going to predict the class of that face. That is whether that face is of mine or other person's. Right, and we're going to have class probabilities, and based on that we'll take that and use non-max suppression to get this final outputs, right? So there is a car here, and then based on this non-max suppression, the highest confidence, you're going to get this grid cells. So so as you can see here, this is the output. So the overall output of this model will be this. So S by S, because we are going to doing it for each grid cell, right? So each grid cell will have this value, and if you look at all of these grid cells, we are going to have this value S by S into here. B is nothing but the number of bounding boxes again. So I forgot to say that too. So for each grid cell, we are going to have two bounding boxes, and the bounding box with the highest confidence will be, or highest IOU will be considered. So, and an important thing is there is a limitation for a YOLO algorithm. Each grid box and can only have one object. So let's say you have one cycle and yeah, let's say you have a part of cycle and part of cat. That is a limitation for the YOLO algorithm. So therefore, choose the smallest bit size. Right. So we'll have bounding boxes, and then we are multiplying by that by 5, because we have um 5 values, that is x, y, width, height, and then the confidence, and then we'd also have plus C. So C is nothing but the class probabilities. So the probability of that object being of, let's say, 20 classes or 30 classes. So this YOLO algorithm of this paper is trained on a data set called Pascal dataset. So it has 20 classes, right? So the Pascal dataset has 20 classes, and then the output prediction of this YOLO algorithm will be 7 by 7 into 30. Let's see what's going on. This is the paper. You can just read through it. You can understand this. Right. Good. Now let's get to the neural network design. So until now we have talked about the basic overall inputs and outputs of this YOLO algorithm. Now let's look at the network design. How is the network of the YOLO algorithm actually designed? So like, hope you understand what is going on here. Just go through this algorithm. You can just pause this video, go here and just read it. All right, I think, have I missed anything? I don't think so. Yeah, so yeah, so as you can see here, this is the yeah, this is how we can calculate the confidence, I think. Yeah, so this is how we calculate the confidence, and then this diagram, and this is the output of this YOLO algorithm. The overall output, we have S by S cells, and then we have B into 5 plus 7 for each output, and we are going to have several bounding boxes. Let's say 2 in this case, and then the best bounding box we're going to have the bounding box with the most confidence will be considered. So each grid cell will predict B bounding boxes and confidence score for this box. So each bounding box is going to have its own confidence score, and then yeah, each bounding box will have its own XY. Each and also its own width and height. So essentially, each grid cell will predict a bounding box of that specific object that is on that specific grid cell, right? That, so these confidence scores reflect how confident the model is that the box contain object, and also how accurate it thinks that the box it predicts, right? And then yeah, you can read to that. Now let's get to this architecture design. How is the CNN designed? So as you know, like if you want to build a CNN that can let's say classify between images, you don't have to have many number of layers. Right, so the problem is pretty simple, right? So in terms of image classification, let's say you want to build make a human, let's say, understand the differences between two objects, like visually, in the sense of visually, it is actually very easy, but now we are having multiple parameters, like we want our model to predict multiple parameters, right? So therefore, in order for our model to predict multiple parameters such as location, the class size, and also the like predicting the width and height, thus we need many more layers compared to this um, image classification problem. So therefore, we'll have many layers. As you can see here, like I just counted, there are many more than there are many layers. So I'm just going to go through this very fastly. So we have for the first convolutional layer, and the kernel size, the size of this kernel is 7 by 7, and we are going to have 64 kernels. So we are going to have 64 neurons in sense of neural networks, and then so each the size of each weight or the size of each kernel is going to be 7 by 7, and then we are going to have a stride of 2. I'm going to explain very fastly what is a stride is. I have forgot that in this in last videos. So let's say you have image and you're performing CNN operation. So normally in a CNN, you just shift this box by 1 pixel, right? So you have this sliding window, and then you just shift this window, this kernel by 1 pixel. But if you have stride of 2, you just shift this by 2 pixels. That is the idea of strides. And then we have yeah, that is strides. And then the first convolution layer, as I told you, 7 by 7. It is the size of this kernel, 64 kernels. And then max pooling layer, again 2 by 2, stride is equal to 2. And then we'll have another convolution and layer, 3 by 3 here. Now the size of this kernel is 3 by 3, and we'll have 192 kernels. And then again max pooling, 2 by 2, stride 2. And then now look at this. We'll have one by one convolution layers. So one by one convolution layers. I've already explained the use of one convolution layers in the video of inception, right? So we'll have one by one convolution layers in order to decrease the size of this image and also decrease the computation power required. So one by one convolutional layer, because you don't have to update a lot of parameters. You'll only have one number which will be updating, and this number will be shared to all of these pixels. And then again we'll have 3 by 3 size kernel, again multiply by 256. We're going to have 256 3 by 3 kernels, and again 256 1 by 1 kernels, 512 3 by 3 kernels, max pooling layer. And then again we have 1 by 1 kernels, 256 3 by 3 512. And then we are going to repeat these kernels right? So we are going to have 1 by 1 256 3 by 3 512, and then again 1 by 1 256, and we're going to repeat that by 4 times. So just like you can experiment by changing number of CNN layers and number of neurons, aka kernels. And then we'll have many CNN layers, and finally we'll convert this CNN layers into some uh, like a we will have neural network, a normal neural network. And then the output is, and then after we get this output of this neural network, we'll reshape this output into a 7 by 7 into 30 output. Again, all of these parameters are optimized. Just so all of these parameters inside of this neural network, there are many parameters. All of this will be updated, and then the final output of our network is 7 by 7 by 30, right? So we are going to have 7 by 7 for each, and then we're going to have 30. So where did this 30 come from? We can just calculate it. What is S is 7. So we're going to have, so this is going to be b into 5 plus c is going to be 30. So C is 20, B is 2, 2 into 5, 10 plus 20, 30. And then as the neural network, so again, look at this CNN, we are going to perform this CNN operation for each grid cell. So we are going to have this CNN outputting its values for each grid cell. Sorry, each grid cell we are going to have a CNN, or this CNN we are going to use for each grid cell. So output is yeah, 7 by 7 S by S into B plus 5 plus C, right? If B plus 5 into C, right? You can calculate it. It will be 7 by 7 by 7 into 7 into 30. Now let's build this network. Let's just build this network just so you can understand. It's just an exercise. You can just pause this video and just build this network. Let's go to Google Colab. Just pause this video if you want to, and just go and build this network, right? I'm just take my mouse there. So you can just open Google Colab, um, right? I'll create a new notebook. I'll just say new notebook, right? um I think that's it. And then we are first we'll develop this CNN, and then after that, after we develop this CNN, let's look at the loss function first. Yeah. So you can develop a neural network using a data set, but for the case of this video, we just need to understand the architecture and all that. For the case of this video, we'll just do it normally. All right. So first, what is the CNN layer? First, we'll initialize TensorFlow. We'll just import TensorFlow because that is the only thing we need. I'm going to say TensorFlow, STF, and then let's initialize a model. So in this video, I'll introduce you to I'll introduce you to I'll introduce you to a new style of model building by adding layers. So it's just tf.model.sequential, right? Sorry. Yeah. So yeah, I can just do this. Sorry for that. And then I can just add layers. So I can just say I'll add the first layer. What is the first layer? We'll have this CNN layer. So what is the CNN layer here? We have kernel size of 7 by 7 and we have 64 kernels. I can just say model adapt tier.keras dot layers dot con 2D. This is 2D convolutional layer because the size of the kernel is two-dimensional. I'll have 64 kernels and 7 by 7. And the input size, what is the input size? Input shape, I think. What is the input shape? Think about it. What will be the input shape? It will be 7 by 7, right? Right. It will be, let's just see what, like, it will be 7 by 7. I'm just going to remove that. Sorry. Good. So, the input shape will be 7 by 7. Then the activation, you could use activation function. I think I'll use the ReLU activation function. I think in the research paper they use leaky ReLU, which is also another type of ReLU in which you set the slope and all that. So we have activation equals ReLU, and then let's do the other layer, and we should also specify the stride, right? I think that's this bit, right? Stride equals 2 by 2, right? And then let's add the next layer, max pooling layer, max pool 2D. We have how many, like we'll have the stride equals 2, and then what else? So we have stride equals 2, and yeah, we have a 2 by 2 max pooling layer. uh, I think that is a default, so we'll have stride equals 2, and then let's add the next layer. I can just copy this and repeat this again. Let's see, it shall be. Then we have what we have 3 by 3 kernel size, 192 configurational layers. So I'm just going to say 192 3 by 3, and I don't need to specify the input shape. Just specify that for the first layer, and then we're going to have do this try two, and then let's add the next layer. We're going to add layers.con 2D, and I know what I'll just import the I'll just do this. You don't have to write tf.keras.layers.con 2D. You can just do this keras.layers.layers import con 2D. So by importing like this, you don't have to type the whole tf.keras.layers.con 2D. You can just say con 2D, right? And then I can just say what is the number of convolutions. It is 1 by 1 128, 128, 128, 1 by 1. Is there a stride? There is no stride. That's it. And 3 by 3 256. Just do this again. Activation equals value, and you get the idea, right? You can just add like this today. Then what? I think 3 by 3 256, 3 by 3 activation equals value, and so on, right? You get the idea, right? So you can create a model like this, and then let's say, and I'm going to skip this part because it is a lot of hard coding, right? You can just look at this model. You can also implement this. Sorry, I've run this. Okay, so you can also implement it. You can add many number of CNN layers, or the number of CNN layers as specified in this paper. And then after that, what we'll do, we'll just flatten this layer. So let's add a flatten layer. Like I'm just going to leave these hashes just to show you that you can add all of these layers. And then let's add a flatten layer. Flatten. In order to input this output of this CNN to a neural network, we have to convert this two-dimensional output into single-dimensional vector so that we can do this neural network thing. Right? I'm going to do this flatten layer. Then let's add the neural network. So okay, I'm going to say tf.keras.layers.dense. So how many neurons should we have as the output? Well, let's just look at the calculators. What is 7 into 7 into 30? So here 7 into 7 into 30 will be the output of this CNN for each grid cell. So we're going to have 1470. I'll add 1470 neurons with activation. Let's say ReLU. I don't think we need activation, right? So we'll have 1470 neurons, and then finally we will reshape this output. So we'll reshape this output into a 7 by 7 by 30. I think I could just do that. 30. Understand? Okay, so we'll have this output dense layer will to be 1470, because the required output for each grid cell is 7 into 7 into 30, right? And the output of and the multiplicative and the product of 7 and 7 into 30 is 1470. So I'm just going to put 1470 there, and then finally we are going to reshape this output to be a three-dimensional matrix as said in this paper. So that is the overall architecture of this model. Again, you can just add all the CNNs, and you can also do the pre-processing yourself. I have described this part, right? Like all this part is like pre-processing. How you can pre-process this image. First you have to take this image and do some simple Python, like looping this to that image, and dividing S by S boxes. Again you can select S to be whatever number that you want. In this paper they have used S to be 7, right? And then you can do this for each for each grid cell model, you can just input, yeah, for this CNN model, you can input each grid cell, and then you can get an output, and then finally you can use non-max suppression to get this final output. So we'll have this is the overall CNN architecture that is used in the YOLO algorithm. Now let's look at the loss function. What will be the loss function? It is actually it actually includes a little more complex process. It's not very simple. So this is the loss function. Yeah, this is all a mathematical equation. Here I'm just going to first explain you the notation. What is the notation on all that? Here x is the x value, the x coordinate of the midpoint for each grid cell, of course. And then so xi is the actual target, right? In the case of training, we'll already have the target values, which is the actual values. So which will be the actual x, y, w, and h for each grid cell. And then we are going to uh, and x hat is nothing but the predicted value, the value that will predict. Y is also the actual value, and y hat will be is the predicted value. And here you might guess wi is the actual value, double hat I is the predicted value, and so on for h also. And here c is nothing but the confidence score, confidence whether there is an object in that particular grid cell or not. And then C hat is the actual, C hat is the prediction. And here Pi of C is nothing but, I think, the class probability, probability for each class, the actual probability for each class. And then P hat I is the predicted probabilities for each class. And then as you can see here, lambda quad is nothing but a parameter. It's a constant. You can set whatever you want. So this variables, this lambda quad and this land yeah, this lambda quad specifies how much importance you should give for each term. So let's say you have this term first, you have this term again. So how much important you have to, how much importance you have to give for each class will be defined by these lambdas. So let's say you want this term to be as high as possible. Let's say you want to have this term to have the highest amount of importance. Let's say this is the function that you want to minimize the most. Then you can set this lambda quad to the highest value. And then let's say you want this term to have lowest value, let's say, then you can just put less number here in order to balance and trade off these important parameters, important functions, right? Important function of this output model. As you can see here, we'll loop through S. So we'll loop through all of these grid cells, and then we'll loop through all of these bounding boxes. For each bounding box, we are going to calculate this value, and then we are going to add off all these values for all of these grid cells, right? And then we are going to multiply that by lambda quad. I think in the paper they have used 5. Let's just see what they have used. They have used 5. I think they have used 5 as the first lambda quad, and you can just set any value according to the problem that you are solving. How much important are these values for you? And then we're going to find essentially the distance between each of this, right? Euclidean distance. And then we're going to do this. We're going to do the same thing. We are going to loop through all of these grid cells, and we're going to loop through all of these boxes of each grid cell, and then we're going to add the values. So again, look, as you can look here, we are getting the square roots, because W can be higher values relative to this X value. So X value is going to be relatively smaller compared to this W value. So we are going to square root, we're going to get the square root of Wi just to make sure that the difference is smaller, because yeah, larger values will have larger difference. So therefore we're going to get the square root in order to decrease the values. I think that is the thing why you square root it, right? And then after that, after we have calculated the loss function for x, y, w, and h, the actual loss function, we are going to do this for confidence score also. So as I've already told you, each bounding box prediction for each grid cell, so or each prediction for each grid cell, we have 5 values, right? X, Y, W, H, and the confidence score. And then we are going to do the same thing for confidence score also. But as you can observe here, we have 2 terms for confidence scores. So I'll explain what is that. So if you have an object, if ci is actually if there is an object in this in that particular grid cell, if there is an object in that particular grid cell, this I think, yeah, this thing will, this um so this term will be calculated if there is an object in that particular grid cell. If and if there is no object in that particular grid cell, this term will be run, this term will be calculated, and this term will not be calculated. So there is no difference, both of these are pretty same. Then after we have calculated the loss function or the prediction, or how good the prediction of confidence was, we'll calculate the we'll calculate the we'll evaluate the classes, right? So we'll just use a normal max um, mean squared error loss. We'll just subtract all of these probabilities, the actual and the target probabilities, and then we'll just square it, and we'll calculate this for each class, and then we're going to add them, right? We're going to add the difference between probabilities for each class, and we're going to add that for all the classes, and then we're going to do this for each grid cell. So this loss function is for all of this grid cell. We are going to get, so the output of CNNs will be output for all of these grid cells, and they're going to calculate this loss function, therefore for all of these grid cells. So that is a loss function, actually pretty simple. Visually that might look pretty complex, but it's actually pretty simple. Again I'll put the research paper in the description below. Make sure to check that out. And feel free to implement your own YOLO algorithm for your own problem. A good thing is to go through a website called Kaggle. Just go through kaggle.com. Very good website. I have already described this website in probably an earlier video. Just go through this website and I search for object detection. Object detection. Right? So left, let's say, yeah, let's say car object detection, let's say. And you can just create a new notebook and start getting those images, doing the pre-processing, and then building this YOLO algorithm by yourself. So I'll definitely encourage you to do this project. And after, I think, I think in the next video, in the future videos, I'll probably do the YOLO object detection. We will use this YOLO algorithm to, let's say, predict the object with, let's say doing car object detection. We will use this algorithm to do car object detection. So thank you for watching, and then I'll see you in the next video.